Hello everyone. In the previous lecture, we've been through Lagrange's theorem. We have presented a proof of this theorem. Uh, so while going through the proof, we introduced an equivalence relation as here, right? And then we counted certain number of cosets and so on in order to obtain the statement that the the order of a subgroup H divides the order of the I mean if you have a subgroup H of a group G, then the order of H divides the order of group or divides the order of the group G. So this holds under the hypothesis that G is a finite group. This is usually phrased as the order of a subgroup divides the order of a group. Okay. Then we had stated certain exercises and examples. So I hope you have been through this. If not, then please make sure that you go through all of this. Yeah. So while going through this proof, we have, or maybe a while before the proof, we have met this notion of left cosets, and in an analogous manner, we have also made this notion of right cosets of a subgroup H of a group G. So this notion holds not only in the situation when G is finite, but one can also discuss this notion of left cosets and right cosets even when G is infinite. Okay, and H is finite or infinite, anything is okay. Okay, great. So we'll try to understand this notation a bit better. We'll go through certain examples. Okay. So you start with a subgroup H of a group G, and then just to recall that we have this notion of left cosets and right cosets. We have this little g times H for an element little g inside G, and this is called the left cosets. This is called the left coset. This consists of the multiples of the element G, by elements from the subgroup H from the right. Okay, from the right. Okay, fine. And the notion of right cosets is quite analogous to this. The notion of the right cosets, the right coset given a subgroup H of G, then a right coset corresponding to an element G consists of the multiples of the element G by elements of H from the left. Okay. Uh, you may say that, I mean, yeah, so why when you put H in the left we should call it left coset? No, I mean the convention that we are following is that if you put little g towards the right, then we will call it a right coset. Okay. And sometime you may get to see that this is denoted by H dot G or maybe G dot H, something like that. That's fine. This is just to indicate the compositional law of the underlying group. For instance, if the compositional law of the group is denoted by the symbol star, then sometime H is denoted by H star G, and similarly GH is denoted by G star H, etc. Okay. Fine. And yeah, so just one more quick thing to recall. So if you have a group G, if you have a group G and an element X inside the group G, then if you collect all the elements of G, which can be expressed as a power of X, as an integral power of X, then what you get is a subgroup, and this is known as the subgroup generated by X. This is generated by X within angle brackets. Okay, maybe I should have put two dots here, that the symbol is defined to be the subset of elements of G which can be expressed as an integral power of X. And this is not only a subset of G, but it also forms a subgroup of the group G. Okay. So now we are going to understand or this review these notions, namely the notion of subgroup generated by an element X, the notion of left coset, and the notion of right coset through certain examples. Okay, through one of the through certain examples. Whereas the ambient group will take one of our most favorite examples, namely Z mod n Z for certain specific values of n. Okay, just to make ourselves comfortable, or maybe just to elaborate it in a really detailed manner. Okay. So this example deals with the group Z mod 3Z and asks to describe the subgroup of Z mod 3Z generated by an element X. Okay, generated by for each and every element X. So we have to, for each element X, we have to determine the subgroup or to describe the subgroup of Z mod 3Z generated by the element X. Certainly we can write this symbol, but this is not a description, right? This is just a notation. Okay. Yeah. So let's note that Z mod 3Z is a group, right? It's a group of order 3. So it has got exactly 3 elements. Its elements are 0 and 1 bar and 2 bar, okay? And we can look at the subgroup generated by 0. So you have to collect all the powers. So 0 bar, power n, etc. So which is to collect 0 bar power n, which is 0 bar added with itself in times, okay, at when n is positive, okay, and when n is negative and so on. You can try to go through the definition of g power n, okay, to see that the subgroup of Z mod 3Z generated by 0 bar, which is generated by 0 bar within angle brackets, is equal to the singleton set consisting of the element 0 bar only, okay. And then in that case, then if you look at the left cosets of 0 bar inside Z mod 3Z, they are what? So if you go back to the go back to this very first page. So then the left coset corresponding to an element little g is little g times h, okay. So that is little g composed h, so which is little g plus h in the context of Z mod 3Z. So you have to collect little g plus h. So, and this has to be done for all h inside h, right? So you have to look at the elements of the form little g plus h, where little h varies across the subgroup h, right? Okay, so yep. So here, we need to add this little g, okay? So just recall that I mentioned that little g times h is sometimes denoted as g star h. So you have to calculate, or you need to understand what is little g plus h here. So what are the choices for little g? So little g could be 0 bar, or it could be 1 bar, or it could be 2 bar. So here I have written all the choices for little g. Then you add h to that, right? So you have to write g plus h, okay? So here is your g, the element 0 bar, and here is your h, so which is this, okay? And now 0 bar plus the subgroup generated by, this subgroup h is by definition 0 bar plus all elements of h, okay. I'm just writing this in a naive manner only, okay. This is naive, okay. This is not acceptable. This is not how to say, this is not precise or not accurate, something like that, okay. Just for notation, there are things which are allowed to do on the blackboard, okay. But as you see, when I write using this marker, I write very briefly. But to write a precise solution, things has to be put in sentences, okay. This is what I was just trying to point out, okay. So please be careful with all that, okay. Anyway, so this g plus h, so you have to add 0 bar, to this element 0 bar, you have to add all elements of this subgroup, and there is only one element inside this subgroup, namely 0 bar. So you end up getting just 0 bar, and then to this element 1 bar, you have to add all elements of this. So that is just, you have to add 0 bar, so you'll get 1 bar. And similarly, 2 bar plus 0 bar is 2 bar. And here, so you have calculated all the cosets, and let's see whether they're the same or not. You see that they're singleton set consisting of this distinct elements 0 bar, 1 bar, and 2 bar. So we observe that these cosets are all distinct, right? So what you have seen is that if you look at the subgroup of Z mod 3Z generated by the element 0, okay, then this subgroup generated by 0 bar of Z mod 3Z has exactly 3 distinct left cosets. Fine. So now we need to repeat the same thing for 1 bar and for 2 bar. So if you look at the element 1 bar of Z mod 3Z, and you look at the subgroup of Z mod 3Z generated by 1 bar, then you have to collect 1 bar raised to n, okay. And raised to, in the sense, 1 bar composed with itself n times when n is positive, and when n is negative, you know what to do. So you have to have 1 bar, and then you have to have 1 bar plus 1 bar, which is 2 bar, and then you have to have 1 bar plus 1 bar plus 1 bar, which is 3 bar, which is same as 0 bar, right? So the subgroup of Z mod 3Z generated by 1 bar consists of 0 bar, 1 bar, and 2 bar, these 3 elements, which is exactly equal to Z mod 3Z, okay, which is equal to Z mod 3Z. So please do not say things like exactly equal to. When you say equal to, it means it is exactly equal to. I'm sorry for using that term exactly. This is equal to Z mod 3Z. So we see that, and now now we study the left cosets of this subgroup. So we have to look at 0 bar plus 1 bar. So which is 0 bar plus this by definition. So now you have to add 0 bar to this element, then 0 bar, you have to add 0 bar to this element, then you have to add 0 bar to this element, okay? Then you will end up getting 1 bar and 2 bar and 0 bar. So it's exactly equal to, which is equal to Z mod 3Z. Now for the left coset of the subgroup corresponding to the element 1 bar is a set consisting of the sum of 1 bar and sum of 1 bar and 1 bar 1 bar with 2 bar and then 1 bar with 0 bar. So which is 2 bar 0 bar 1 bar, so which is Z equal to Z mod 3Z. Now the left coset of this subgroup corresponding to the element 2 bar is the set obtained by, the set consisting of the sum of 2 bar with 1 bar and then 2 bar with 2 bar and then 2 bar with 0 bar, which is 0 bar 1 bar 2 bar, which is equal to Z mod 3Z. Right? So in the previous case we saw that the left cosets of this subgroup that you obtain corresponding to these elements, they are all distinct, right? But in this case what you see is that the left cosets corresponding to all these three elements, they are all equal to Z mod 3Z. Okay, so these cosets are all equal to each other. Okay, thus there is only one left coset of this subgroup. Okay, so yeah, so this GH is a coset. Okay, so you cannot extract G from there. Okay, so this is something that you can observe. So if I give you G times H, okay, note that from this symbol you can say that I know what is little g, right? But no, this symbol is a set. The symbol is a set, so so this is similar to the situation what you learn while learning trigonometry. From sine theta you cannot extract theta, although sine theta as a single, if it is given as a single gadget, right? And sine theta is a single gadget, it's a single number, right? So although while writing you do get a chance to write theta, but but you do not know what is theta, right? So for example, sine 30 is same as now I don't know, I've forgotten all this. Sine 30, okay, let me write it with cos. Sine is the perpendicular, okay, so with cos things will be fine. So for example, cos 30 degree is cos minus 30 degree, right? But yeah, but it doesn't mean that 30 degree is equal to minus 30 degree, right? Yeah. So what you see is that these left cosets are all equal to each other, okay, and thus there is only one left coset of the subgroup of Z mod 3Z generated by 1 bar. Okay, now you can do the same thing for the subgroup of Z mod 3Z generated by the element 2 bar. You will again get to see that these cosets are all equal. Oops, I'm so sorry. The correction is that this has to be 2 bar. Okay. This has to be 2 bar. Okay, this has to be 2 bar 2 bar 2 bar. So you can also check the computations. And you will see that these cosets are all equal to each other. Well, the reason is that the reason is the following. So at least in this case, so here the subgroup that you get, the subgroup of Z mod 3Z that you get may be corresponding to 2 bar, or maybe in the previous case corresponding to 1 bar, that is equal to Z mod 3Z. Okay, that is equal to Z mod 3Z. It was shown that it is Z mod 3Z here, and here also it will be Z mod 3Z, because you'll have 2 bar, and then you'll have 2 bar plus 2 bar, which is 4 bar, which is same as 1 bar, and then you will have 2 bar plus 2 bar plus 2 bar, which is 6 bar, which is same as 0 bar. So you have obtained 0 bar, you have obtained 1 bar, and 2 bar were already there. So you have Z mod 3Z. And now to this set, if you add 0 bar, okay, then this is a subset of Z mod 3Z. This is a subset of Z mod 3Z of size 3, right? There are exactly 3 distinct elements. So if you add some element to all these elements, you will again end up getting a subset of size 3. And any subset of Z mod 3Z of size 3 is equal to Z mod 3Z. Okay. So here you are adding 1 bar to these 2 distinct elements. Then the set that you will get will have exactly 3 elements. So why? This is you can say this is due to the cancellation law. Okay. Because for example, 1 bar plus 2 bar is equal. If 1 bar plus 2 bar is same, if 1 bar plus 2 bar if it were same as 1 bar plus 1 bar, I'm saying that if 1 bar plus 1 bar is same as 1 bar plus 1 bar, then you can cancel these two from the left side to obtain that 2 bar is equal to 1 bar, which is not the case, right? Okay. So here this has to be z mod 3z. Okay. So in other what I'm trying to say, what I was trying to explain is that these cosets, they have to be equal. Okay. So if you have a subgroup, if you have a subgroup, if the subgroup happens to be z mod 3z, then z mod 3z has got only one left coset. More generally, one can say that if G is a group, then then there is only one left coset of the subgroup G of G. Okay, so G certainly can be thought of as a subgroup of G. I mean, indeed G is a subgroup of G. So if you look at the cosets of, or the left cosets of this subgroup, then you will find only one left coset. Okay. Anyway, so now try to continue this exercise further. So for each x inside z mod 4z, we can try to describe the subgroup of z mod 4z generated by the element x, and you can also try to describe the left cosets. So if you look at the subgroup of z mod 4z generated by 0 bar, you again get a similar picture. Okay, similar mathematical picture. Okay, and here these cosets are all distinct, and you see that they're the distinct singleton subsets of z mod 4z. Okay, this is again similar. There is a statement. There is something that one can state analogous to this. For example, if G is a group, or maybe just to keep things somewhat simple in our mind, G is a finite group, then there are exactly, let me write, size of G many distinct left cosets of the subgroups consisting of identity only. Size of G many distinct left cosets of the subgroup this of G. I'm sorry for this bad handwriting, but I hope this is understandable, at least when I'm explaining or reading it out. So if G is a finite group, then there are exactly size of G many distinct left cosets of the subgroup consisting of the identity element. Okay, if you look at this subgroup of G, then it has got exactly size G many distinct left cosets. Okay. Now if you look at the subgroup of Z mod 4Z generated by 1 bar, you'll get the full group, and thus there is exactly one left coset. Okay, thanks to this observation. Okay. Okay, and there sorry, where were we? Yeah. Okay. So there is exactly one left coset because the subgroup is the full group Z mod 4Z. So now if you look at 2 bar, the subgroup how do you say, the subgroup that you get is no more the full group. It's got exactly 2 elements, so its size is half of the size of the group that we had. And here you will see that just doing this elementary computation, there is not much point in explaining you addition. Okay, right? This is something that you can go through and verify, or rather, instead of even going through, you can try to do it on your own. We have already discussed the cases, the case of the group Z mod 3Z. So for Z mod 4Z, it's a good idea to try things on your own. I just try to put these details in these notes in order to make sure that in case you would like to verify what you could do or what you'll end up doing on your own, if you would like to verify, then you have something ready. Okay, great. And here you will see that there are exactly two distinct left cosets. Okay, yeah, and if you look at the subgroup of Z mod 4Z generated by the element 3 bar, then you will end up getting the full group Z mod 4Z, and there will be exactly one left coset. And yep, similar. This happens due to which observation? I think this one. Let me just read. Yeah. Okay, so if you look at the subgroup G of G, and then there is exactly one left coset. And just few more comments. Yeah, you know that G times H is same as H times G when the group G is abelian, right? When the group G is abelian, then you know that GH is same as HG. So you also know that GH is same as HG, okay? Where the H's have to, now earlier we're talking about little h's, now I'm writing capital H, okay? So the left coset, of the subgroup H corresponding to the element G is equal to the right coset of the subgroup H corresponding to the element little g. This holds for any G inside G, okay? I mean, this holds when G is abelian, okay? So when G is abelian, if I'm sorry, it just went off. When if G is abelian, then GH equal to HG for all G inside G, okay? Great. And then yeah, as you were saying, we are trying to understand the notion of left cosets, subgroups for some of our favorite groups, and Z mod NZ happens to be certainly one of our most favorite groups. And then in the previous lecture also, we have seen this group Z mod NZ at least once. For instance, in this exercise, I hope you have thought about this exercise. This exercise asks what happens if you consider the groups mu n and the group Z mod NZ together. So it asks whether are these groups really different? As I explained in the previous lecture, that this question is quite naive, but it's a good time to think about whether these two groups are really different or not. Okay, there is no definite precise answer of this question because the question itself is quite naive, but one can develop certain terminologies and certain notions in order to answer this question in a satisfactory manner. Okay, and that is precise. Okay, but one need to develop certain notion of certain notions, okay, because this phrase really different doesn't make much precise sense, right? One can definitely say that yeah, they're different because this is mu n and this is Z mod nz. Okay, here and this comes from complex numbers where you multiply, and here you quote unquote add, right? So they are different, but still, are they really different? So please think about this. And so we have been dealing with Z mod nz in the for last couple of minutes. So now you can try to repeat the same exercise for the group mu n. Okay, so you can try to solve all these exercises by replacing Z mod nz by mu n, and for the group Z mod nz itself, one can work on some certain further exercises. So here I have just put few exercises for you. So for instance, describe all the subgroups of the group Z mod 3Z, and then work on the same problem for the group Z mod 4Z, and repeat. Try to work on these two exercises, exercises 116 and 117, which is similar to the exercises that we have been discussing today. Okay, let me conclude here.